Assumptions to three-phase induction motor. So we already before that we discussed about the torque, that is the conditions also discussed at starting torque and maximum torque conditions. Here now problems on torque equation. Read once again here. This one read one. Carefully read this one. A 6-pole 50 Hz 3-phase induction motor has rotor resistance standard still, rotor reactance 0.03 ohms and 0.1 ohm. At standard still, the given resistance R2, the rotor resistance is 0.03 and the X2 is 0.1 ohm. This is in for phased. Calculate the value of the external resistance to be connected in the rotor circuit to obtain 80% of the maximum torque at starting. 80% of the maximum torque at starting. Here number of poles given data P is equal to 6, frequency 50 Hz, R 2.03 ohms per phase, X2 is 0.1 ohms per phase. Here starting torque is 80% of maximum torque. That means TST is equal to 80% of T maximum is nothing but T starting by T maximum is equal to 0.8. Now the ratio of starting to maximum torque is, that is TST by T maximum is, that is equal to 2A by 1 plus A square. So here TST by T maximum is 0.8, that is equal to 2A by 1 plus A square. Here 1 plus A square is equal to 2A by 0.A. That means here we could write quadratic equation A square minus 25.A plus 1. So A is equal to under root of minus B plus or minus B square minus 4AC by 2A. This is the formula for quadratic factors we have to determine. So here a is equal to minus of minus 2.5 plus or minus under root of minus 2.5 whole square minus 4 into 1 into 1 divided by 2 into 1. A is equal to 2 or 0.5. Small value of a must be selected here. Why a is always less than 1? So a is equal to a is equal to 0.5. Let R be the external resistance, then R2 plus R be the total resistance. The ratio of rotor circuit standstill resistance A is equal to R2 plus R by X2 is equal to R2 plus R by X2 is equal to 0.5. Here from that R is already known. What is that? R2 is already known, 0.03. We have to determine the external resistance R. So here 0.03 plus R divided by 0.1, that is equal to 0.5. R is equal to 0.5 into 0.1 minus 0.03, that is equal to 0.02 ohms. The external resistance is added to the rotor is 0.02 ohms. Here R2 plus R is 0.03 plus 0.02, that is 0.005. That is the total resistance of the rotor, but external resistance is 0.02. Problem number 2. Read once again it. A 4-pole 50 Hz 7.46 kilowatt motor has a rated voltage and frequency, a starting torque of 160% and maximum torque of 200% of full load torque. Determine full load speed. Second one is speed at maximum torque. Speed at maximum torque. Solution: given data, number of poles P is equal to 4, frequency F is equal to 50 Hz, TST is equal to 160% of full load torque, T maximum is equal to 200% of full load torque. TST by TFL that is equal to 1.6. And T maximum by T full load is 2. Here TST by T maximum is 1.6 by 2, that is equal to 0.8. TST by T maximum is equal to 2A by 1 plus A square, that is equal to 0.8. Here 0.8 A square plus 2A plus 0.8 equal to 0. We get A is equal to 0.04. 0.04. T full load by T maximum is, that is 2ASF A square plus SF square, that is equal to 1 by 2 into 0.04 SF by 0.04 whole square plus SF square, that is equal to 1 by 2. SF is equal to 0.01. Now the synchronous speed ns is equal to 120 F by P, that is equal to 120 into 50 by 4 air poles. Number of poles are 1500 rpm. Number of poles are 4. So 120 into 50 by 4, that is equal to 15 rpm. Full load speed n equal to ns 1 minus sf. ns is 1500 and within bracket 1 minus 0.01, that is 1485 rpm. Slip at maximum torque Sm is equal to R2 by X2, that equal to A equal to 0.04. Speed at maximum torque is N is equal to Ns into 1 minus Sm, that is 1500 1 minus 0.04, that is equal to 1440 rpm. So here advantages of three-phase induction motor. Very simple, extremely rugged and almost unbreakable construction, especially squirrel cage type. Now here another advantage is low cost and highly reliable. It has sufficiently high efficiency, a construction of three-phase induction motor. An induction motor consists of essentially two parts. A stationary part is called stator, a rotating part is called rotor. A rotating magnetic field. The resultant flux is constant magnitude equal to 1.5 times the maximum value of the flux due to any phase in a three-phase supply. The resultant flux rotates around the stator at synchronous speed given by ns is equal to 120 f by p. It is understood that for working of three-phase induction motors, a three-phase revolving flux of constant magnitude and synchronous speed is required. This can be obtained by means of a three-phase supply given to stator conductors. So further, a rotor torque is set up by using Faraday's laws of electromagnetism, that is Fleming's law and Lenz's law. Starting torque K2 is equal to R2 square plus X2 square, and K2 is constant. So here K2 into R2 by Z2 square. Now starting torque is equal to K2 into R2 by R2 square plus X2 square. It is derivative with respect to R2 equal to, the starting torque is derivative with respect to R2 equal to 0. R2 square plus X2 square is equal to R2 square, and here R2 is equal to X2 for maximum. Now starting torque, the starting torque T is equal to K1 as C2 square R2 by R2 square plus SX2 whole square. K1 is equal to 3 by 2 pi ns. T maximum is equal to K1 R2 by X2 E2 square R2 by R2 square plus R2 X2 whole square X2 square. That is equal to K1 E2 square by 2 X2. K1 equal to 3 by 2 pi ns. T maximum is equal to 3 by 2 pi ns into E2 square by 2x2 Newton meter. So this is T is equal to TB 2 by SB plus SB by S plus SB by S by SB. Here TG is P2 by 2 by ns, that is equal to 3 by 2 pi ns S into E2 square R2 by R2 square plus SX2 whole square. And also they written in E1 square. Torque in synchronous watt. Rotor input is equal to rotor power losses by S. So gross output power PM 1 minus S. So Once again we are repeating this for doing the problems. So it is seen that although maximum torque does not depend on R2 at the exactly location of Tmax, it is independent on it. Greater the R2, greater is the value of slip at which the maximum torque occurs. Here, torque is proportional to SV square. In general, the operating torque any slip has maximum torque. So that is equal to 2a s by a square plus s square. TST by T maximum, that is equal to 2R2 x2 by R2 square plus x2 square, that is equal to 2R2 by x2 by 1 plus R2 by x2 whole square, that is equal to a by 1 plus a square. So here, for different value of resistance, they drawn the characteristics between the torque and the slip. Here the slip, torque and the slip for different values of resistance. At the starting, the slip is 1, the speed is 0. For R value, the torque is at the starting is TST, that is TST. Some watts torque is there, that is TST for the R resistance, and speed is 0, slip is 1. If the slip is increasing, not increasing, if speed is increasing, the slip is decreasing, goes on. It is, the torque is gradually increasing up to maximum torque. The slip goes on decreasing. So here, maximum torque to up to maximum torque, after that the speed is decreasing, the speed is increasing, the slip is decreasing, and the torque is decreasing from the maximum torque to 0 level. It goes the similar way, for resistance 4R, or the resistance 4R, the starting torque is compared with the R, it is slightly, it is greater than, so the starting torque is greater than that of the R resistance. So here 4R, by connecting resistance 4R, the starting torque is increased at slip 1. So after that the slip is decreasing, the torque is goes on increasing up to maximum, then it is reduced to 0, and for 6R, the torque is increased from the 4R to 6R. The starting torque increased by using of 6R. After that the maximum torque increased, then torque, after that maximum torque it is decreasing, goes on decreasing. Here what we are observed in this case, by adding of resistance, the starting torque is increasing, but the maximum torque is constant for all resistors. So this is the, so very important. If we want starting torque is high, then we should connect the resistance. the rotor circuit. Then we will improve the starting torque. If we want the torque slip curves, here see the torque slip curves. And starting torque, that means you have grass torque and shaft torque formulas. Here already we read this one, rotor grass output Pm, that is 1 minus S, rotor input P2, rotor grass output Pm by rotor input, that is P2 is equal to 1 minus S, that is N by Ns. As stated earlier, stable operation for an induction motor lies over the linear progression of its torque speed curve. The slope of this straight line depends on mainly on the rotor resistance. Higher the resistance, sharper the slope. This linear relationship between the torque and speed enables us to establish a very simple equation between different parameters of induction motor. This is for speed and torque for different here synchronous what already we discussed. It is clear from the above relation torque is proportional to the rotor input. By defining a new unit of torque instead of the force at radius unit, we can say that the rotor torque equals rotor input. The new unit is synchronous watt. Here summarize calculation of maximum torque, slip at maximum torque and starting torque, full load torque.